So that first part of shifting curves was basically moving things left, right, up or down, or flipping them in symmetry. Let's have a look at a few more ideas. If I multiply the function by a constant number, so that means every y value is going to be multiplied by that constant number. Another way of thinking about it is that the y value is divided by the constant. So again, it's not associated with the x because it's not inside the function x. If you associate it with the y, you have y over k. Now, if k is greater than 1, you will end up with a steeper curve. The curve will get steeper. If it's in between 0 and 1, then the curve will be shallower. Obviously, if it's equal to 1, it's the same curve. And if it's negative, well, that just means we've flipped it upside down, and then we worry about the number to see whether it's steeper or shallower. A way of thinking about it, because it's associated with the y value, this one, is what we've done is we've stretched the curve vertically. So it's like we've grabbed the curve and just pulled on it and pulled it out or pushed it in depending on the constant. If it was greater than 1, so we're making the curve steeper, then that would be like pulling it out. If you think about it, that's going to make a curve steeper if we pull it out. If it's in between 0 and 1, it's like we've pushed the curve in. So that's going to make the curve shallower. Okay. What that means is, because the x values basically are staying the same, we're not doing anything to the x values, we're just playing with the y values, the domain of the new one will remain unchanged. It's the range that may be changed. Whereas if it is a multiple of x, so instead of multiplying the whole function by x, we're just multiplying every x value. Now it's the x value that's affected. Interestingly, k is greater than 1, it still makes the curve steeper. And less than 1 makes the curve shallower. But that's because in reality, look what happens here. Here it's x times k, whereas when we actually associated with the y, it was actually y divided by k. So that means we're going to stretch horizontally. We're going to pull it out or push it in. So greater than 1 makes the curve steeper, means we've pushed the curve in. Because think of I guess a trig curve is probably the easiest way to think about it. Imagine you had a sine curve. So think of that shape. Push it in, you can see how the curve's going to get steeper. Whereas in between 0 and 1, that means we must be pulling the shape out, because that would make it shallower. So in this case, it'd be the domain that might be changed. So an asymptote might move to somewhere else or something like that, but the range won't change because we're not playing with the y values, we're playing with the x values. Reciprocal graphs. If I was to turn a graph upside down, some interesting things happen. The x-intercepts will become asymptotes because it did have a y value of 0, but now it's 1 over 0, which is undefined, so they become asymptotes. And the reverse must be true. If the original graph had a vertical asymptote, then if I turn it upside down, it'll become an x-intercept. Anywhere on the original graph where the y value was greater than 1, if I turn it upside down, it will now become smaller than 1. And again, the reverse would be true. If the original graph was less than 1, it will now be greater than 1. So we can get some interesting graphs there. So okay, let's draw a few of these. On one graph, we're going to draw y equals x. Well, that's the easy one. Y equals a half x. Well, this one I can think of two ways. Is it the function x that I've multiplied by a half, or is it just x I've multiplied by a half by itself? So I could think of it either way. If I think of it as the first way, that it's the whole function, the original function's x, and I'm multiplying the function by a half, that tells me this should be shallower. So I'm pushing it down. Okay. If I think of it the other way, we said in between 0 and 1, if I was playing with the x values, that would have the effect of making it shallow again because I'm pulling the curve out. So either way, there we go, we'll get something like that. So if we think of it as vertical, the y value has been pushed down, so it comes underneath the curve. But if I thought of it as a horizontal one, it's been pulled out, so they're going to the right more. But basically, we have a shallower line, y equals a half x. Steeper, y equals 2x, the same sort of idea. And I guess lines, that's kind of obvious. But that idea flows through to all shapes. So if I was to do the same thing with a parabola, here's y equals x squared. Woo. Okay. If I have a half x squared, in this case, it is times the function. Okay? Because I'm multiplying the function by a half. I'm not multiplying x squared by, I was not multiplying x by a half, because remember x is like inside parentheses and then squared. So it's the whole function that's multiplied by a half. It's the y values that are going to be affected. So it's in between 0 and 1, which will make it shallower. So I should be pushing this parabola down. Whoop. So we'll end up with a parabola that is underneath the original one. All the y values have been pushed down. And we get a shallower parabola. Whereas y equals 2x squared, I should get a steeper parabola, because now I'm pulling all the y values up. There's y equals 2x squared. And we could apply that to any function, that same idea. Here's an interesting one, because we've got what was originally a circle. Okay, so we originally had a circle. The x's I've done nothing with. It's the y's I'm playing with. But remember, the factor that I've played with here is not the 4 on the bottom, because I've got it grouped with the y. And it's like saying it's all squared. So it's actually y on 2 all squared. So every y value I've divided by 2 or multiplied by half, whichever way you want to think about it. But when it was grouped with the y and it was on the bottom, so in this case it's like saying divided by 2. That's a number that is bigger than 1. So I should end up with a steeper curve. That means I'm going to pull my circle out by a factor of 2. Right? So the constant is actually 2. If we stretch it out, then we would end up with our ellipse, like so. And you can double check that the y-intercept, sure enough, if I made x equals 0, y should be 2. So there's my ellipse. Let's do a reciprocal one. So 1 over 2 minus x squared. Well, the original graph is x squared. So I'm just looking at that. What have I done to it? Well, I'm going to reflect it in the x-axis because it's minus x squared. Whoop, there it goes. But then I'm going to shift it up 2 units. Remember, that's not grouped with the x, so it must be grouped with the y. So we're going to go up 2 units. And now I'm going to turn the whole thing upside down. So my x-intercepts will become asymptotes. So at minus root 2 and positive root 2, I've drawn a couple of green asymptotes there. Well, the original graph didn't have any asymptotes that are going to become x-intercepts, so that's not going to happen. But what else do we know? Y is greater than 1 becomes less than 1, so that point 2 will now become a half. And it will still be a turning point, like we did here, but now instead of being a maximum, it'll be a minimum. It'll turn the other way. Now, at somewhere there's a y value of 1. So I've just sort of put a box here to say, look, here, for these x values, they all ended up having, originally, a y value bigger than 1. So my new graph will have a y value smaller than 1. So my new graph will be somewhere in that green rectangle that I've just drawn. And I can do the same underneath. So let's imagine that was where y is negative 1. So the original graph has a, well, I'm talking about absolute value here, but a value of something bigger than 1. So when I turn it upside down, it should go smaller than 1. So it'll be in these rectangles. And then, where it was originally less than 1, should become bigger than 1. So there's the regions my new graph should go. And obviously the point of intersection there is when y is equal to 1, and when you turn 1 upside down, you get 1. So that should be enough now. Remembering curves always bend towards asymptotes, and we get our red graph there. So that must be the graph 1 on 2 minus x squared. Okay. So you can always construct these from the basic graph. X plus 1 on x. Okay. What we do for something like this is, some people call it superpositioning. I think in physics they call it something else again. Interpolation? Anyway. Superpositioning. Okay, there you go. So there's my two graphs, y equals x and y equals 1 on x. And what we're basically going to do is physically add all the y values. But there are key points that you would check. So points of intersection are always good ones, because if they're both of that y value, I've just got to double it. Because if I add them together, I'll get twice that y value. So did I do those ones? Oh, a vertical asymptote's going to stay there. Because if in one graph it was undefined, I can't all of a sudden add that undefined to the other graph. So it's still going to have a vertical asymptote on the y-axis. Okay, so now let's do our point of intersection. So there's 2 points that I now know. It's up to you, of course, how many points you do. You just slide a ruler along and just go, oh, look, that one's 2 millimetres above the x-axis, so I'll add 2 millimetres to the line, and so on. But what we should see is the hyperbola is getting closer and closer to the x-axis. So it's getting closer and closer to 0. Therefore, I'm adding numbers that are getting closer and closer to 0. So I should be getting closer and closer to y equals x, the new graph. So as many points you need, there's a whole heap I ended up plotting. It means you need to get an idea of what the shape's doing and then draw them in. And there's our graph, y equals x plus 1 on x. Isn't it pretty? All right, let's have some fun.